Welcome to this explainer. Today, we're unpacking the fascinating, totally invisible thermal engineering that keeps our pantry staples fresh for months on end. I mean, have you ever actually stopped to wonder how a simple bag of dried pasta or that jar of instant coffee can just sit on a shelf for a year without spoiling? It's not just about leaving food out in the sun to bake. No, it relies on an incredibly complex, deeply calculated scientific process. Let's get into it.
Here's our roadmap for this explainer. First, we'll cover exactly why we dry food. Then, we'll hit the science of psychrometrics, the mechanics of moisture, the drying curve, factors that affect drying speed, and finally, the massive industrial equipment that makes it all happen.
Part 1. Why we dry food. Preserving the pantry.
So, the absolutely crucial point here is that dehydration is a highly controlled thermal process. It's totally distinct from just, say, baking a cake or mechanically squeezing water out of a sponge. We are applying heat with absolute pinpoint precision to force moisture out through evaporation or sublimation. We're purposefully altering the food's biological timeline. And removing this water, it's a real game changer. It doesn't just stop rapid spoilage by halting microbial growth and shutting down enzyme activity. It fundamentally changes the entire logistics of our global food supply. By dropping all that heavy water weight, foods like coffee, pasta, spices, and industrial ingredients like egg powder or lactose become incredibly cheap and easy to transport all over the world.
Section 2. The science of psychrometrics. The invisible battle.
Now, I know this might look a bit intimidating at first glance, but the psychrometric chart is basically the ultimate cheat sheet for food engineers. It maps out the exact capacity of air to remove moisture, showing us this delicate dance between absolute humidity, air temperature, and airflow. Engineers use this crazy web of lines to find the absolute perfect atmospheric sweet spot to pull water out of food. A really key concept on that chart is the dew point. Think of the air around us as a giant sponge. Well, the dew point is the exact temperature where that sponge is 100% full of water. If you cool the air past this critical dew point, the water literally drops right out of the air as condensation. So when we're drying food, we have to constantly ensure our hot air never hits this saturation limit. Otherwise, we'd just be sweating water right back onto the food, completely defeating the purpose. Moving on to Section 3, the mechanics of moisture, escaping the food cell.
Okay, I want you to imagine a stubborn, invisible blanket of moist air constantly surrounding a piece of food. Engineers call this the boundary film. To dry the food, a water vapor pressure gradient acts as the driving force. It quite literally pushes the moisture from deep inside the food's cells out through that thick boundary film and into the surrounding dry air. It's basically a microscopic tug of war between the moisture trapped inside the food and the dry air trying its hardest to pull it away.
So how do we actually blast away that stubborn boundary film to maximize evaporation? Well, we need 3 very specific conditions to work in perfect harmony. First, a moderately high dry bulb temperature, which gives us the heat energy we need. Second, low relative humidity, meaning the air is super thirsty and ready to absorb water. And third, high air velocity. Fast-moving air physically strips away that boundary film, thinning it right out so the moisture can escape way faster.
Section 4. The drying curve, when water fights back.
If you trace this curve with me, it reveals a pretty interesting story of increasing resistance. At first, you see this sharp, steady drop where moisture leaves the surface super easily. But then, right here, the line swoops into a long, slow curve. This is where extracting water becomes a real struggle. The surface water is totally gone, and now we're fighting to pull water out from the deep interior of the food.
These two phases actually operate very differently. We have the constant rate period versus the falling rate period. In the constant rate phase, the food acts exactly like a wet bulb. Water evaporates rapidly right off the surface, which keeps the food nice and cool. But in the falling rate period, that's when things get tricky. The surface dries out and internal mass transfer controls the speed. The surface temperature actually starts to rise to match the hot air, which creates a massive risk of heat damaging the food. Nobody wants burnt, dried-out food, right?
That brings us to Section 5. Factors affecting drying speed. Size, structure, and spacing.
To bypass that risk of heat damage, we can actually physically hack the food's structure. By cutting food into smaller pieces, we increase the surface area, giving the moisture a much shorter, easier path to escape. We can even intentionally rupture the food cells through blanching. Engineers also take advantage of something called fiber orientation. Did you know moisture travels way faster along the length of celery fibers or meat proteins than it does across them? It's true. Now, it's a bit of a trade-off because breaking these cells does change the texture of the food when you finally rehydrate it at home.
So all of this brings up the ultimate engineering challenge. We know the thermodynamics, we understand the cellular structure, but how on earth do we take these precise scientific rules and build machines big enough to feed the entire world? Let's find out in Section 6, Industrial Drying Equipment, Machines of Preservation.
Applying this on a massive global scale means different foods require completely different, truly massive machines. For instance, simple bin dryers just pass hot air up through a deep bed of food, which is perfect for cheap end-of-line finishing. Fluidized bed dryers, on the other hand, they blow hot air so powerfully from below that the food literally floats and violently agitates in midair. This exposes the maximum amount of surface area. And for liquids? For liquids, we turn to the magnificent spray dryers.
For liquid foods like milk or instant coffee, spray dryers really are the ultimate tool, and they rely on these incredible devices called atomizers. Whether it's a centrifugal disc spinning so incredibly fast it flings the liquid into a fine mist, or ultrasonic nozzles that literally use sound waves to induce cavitation, the goal is exactly the same. They blast the liquid into microscopic droplets, allowing the hot air to dry them into a fine powder in just a fraction of a second. It's almost like magic.
So what's the ultimate takeaway from this explainer? It's that dehydrating food isn't simply about blasting it with intense heat. It's a highly delicate, deeply calculated battle. Engineers are constantly walking a tightrope between efficiently removing water and perfectly preserving the food's cellular quality, especially trying to avoid heat damage during that dangerous falling rate period. So next time you brew a quick cup of instant coffee or boil some dry pasta, ask yourself, what invisible thermal battles were fought just to keep this food waiting perfectly on the shelf for you?